So let's get started.
Oh, really?
So today I'm going to talk to you about linear models, and what I want to try and do is first persuade you that pretty much every statistical analysis you've ever done, other than maybe graphics, involves fitting a model of some sort of another. Even just calculating a simple mean of observations in a group involves fitting a model in which all of the observations are scattered around some average, which we estimate. And today I'm going to focus on linear models, and we'll talk about some other kinds of models later on. So I'm going to start by telling you exactly what a linear model is, and then go through sort of a variety of topics related to linear models and how we might apply them. And then that's what we're going to be doing in the workshop on Thursday. Oops. So what's a linear model? A linear model is anything that can be written in this way. It involves data. A variable y, a response variable y, can be described as the sum of the contributions of some x variables, 0, 1, 2, however many, plus some random error. And the betas are the parameters of this linear model. So these are the things we try to estimate to gauge or measure the importance of each of those variables in predicting the response variable. So here's a variety of linear models. Simply calculating a mean and fitting it to data involves basically the simplest possible linear model. Calculating an average is an example. We would all probably think, if I asked you to guess what would be a reasonable linear model, we would probably include linear regression. And it's true, linear regression is a linear model. It's sort of one step more complicated than fitting an average, because we include one explanatory variable x. Multiple regression just extends this to multiple x variables. Quadratic regression is also a linear model because it can be written in exactly the same way as the sum of the effects of a bunch of variables. One of those variables happens to be this one squared, but it nevertheless remains a linear model. Now, what I'm going to also do is try to explain to you how single factor ANOVA is also a linear model. But they're all the same thing. ANOVA, analysis of covariance, regression, calculating an average, they're all more or less doing the same thing. They're fitting linear models. And sort of knowing this, I think, will aid in your ability to use the toolkit that's available in R for analyzing models of arbitrary complexity. So some of the methods that we've learned in our introductory course, like fitting different means to two groups, two-sample t-tests, that's a linear model. A multi-factor analysis of variance, linear model. Analysis of covariance, just another kind of linear model. They can all be written in this form. And so the same sort of analytical methods are available to analyze them. And as I mentioned, in the case of the quadratic, a linear model needn't be a straight line.
Why are we using the terminology linear model? Why do we call them linear models? Like, instead of just saying like ANOVA and
Could you repeat that last bit again?
instead of just calling it as a mean or a simple linear regression, why put them under the thing of simple
Linear models. I can tell you. Here's why. Linear models are... I didn't plan this question. So, calling everything linear models sort of emphasizes the fundamental similarity between all of these approaches. Two-sample t-test, one-sample t-test, paired t-test, and so on. And in doing so, it provides a common set of tools. And in R, we're going to learn how to use the LM function. And it's what you would use to fit any kind of linear model, all the ones that I've described. And since they're all more or less the same thing, the toolkit is flexible. It can handle all kinds of different study designs. And LM in R has tools general tools available to estimate parameters like magnitudes of effects, what I think of as biological significance rather than statistical significance, calculating confidence intervals for effects, and so on. It's easy to use even when there's even when there are multiple variables, even when there are missing data points, when your design is unbalanced. In the old days, we used to have formulas to calculate effects and elements for ANOVA tables, but we don't do that anymore. That's what I learned when I was a graduate student. We don't do that anymore. All these traditional ANOVA calculations, they don't work for unbalanced designs anyway. So linear models provides you with a general set of tools. So what I'm going to do is I'm going to show you a couple of familiar applications of this toolkit, linear models, in situations that you're already familiar with. And one is just simple linear regression, and the other one's going to be analysis of variance. So simple linear regression, again, a y and an x, and we're trying to look at the extent to which we can predict one variable from another and how steep is that relationship. And this is a bird data set, a study done on chickadees. So, you know, you all heard black-capped chickadees out there. They sing, they make notes, E-D-E-D-D, you hear frequently. You probably thought they were just spouting nonsense, but actually there's information, as it turned out, in the number of Ds that they emit. So this group went out to black-capped chickadee flocks and they confronted them with stuffed specimens of these different predatory birds. And the predatory birds range greatly in body size, from big and fat to very small. And when it comes to size, the most dangerous predator to a black-capped chickadee, which is about this big, are the smallest ones. And the really big ones are no danger at all to a black-capped chickadee, easy to evade. And so they just recorded sort of the average number of D notes that were emitted by chickadees in the presence of these different stuffed animals. And here I plotted the results of their study in a scatter plot. So D's per call, predator body mass, each dot is a different predator, all done on black-capped chickadees. And there seems to be some kind of an association. And what we would like to do is to fit a linear model, in this case with two parameters, beta naught, which is the intercept, and beta 1, which is the slope. So the betas represent the true values, but what we're going to try and do with data is estimate those values using the B. So I'll use B to indicate the estimate and beta to indicate the truth, the real relationship that's out there that we'll attempt to estimate. So I've got some R code here as to how you would fit this to the data. So we have two variables illustrated here, predator body mass, and then number of D notes per call, and I arranged them in columns. And how we would instruct R to fit that is that we would put the Y variable here, and then a tilde, the X variable. And the method sort of fits the model here, applies the lm command, and then stores the result in this object that I'll just call Z. And then we apply functions to Z in order to extract all the bits that we want. That's sort of the way that R works. And in this statement, the intercept is implicit. So we don't have to include the word intercept in our model if we don't want. It's assumed to be there. And we have to apply a special way if we want to remove it. So it's generally assumed. So there's the equation that we will be fitting to the data, and we use least squares. You know, we sort of imagine drawing all possible lines through this scatter of points, and we choose the values of B0, B0, and B1 that minimize the sums of squares. So each of these data points has a residual. The sum of squared of those residuals is what's minimized in finding the best estimate of slope and intercept. Does that sound familiar? You learned what least squares meant in your introductory stats. So one of the things that I want you to, what I want to hardwire in you when using R is to use summary to get parameter estimates and not to fit or calculate p-values. So from now on, ignore these columns when you use summary, and then use another function, ANOVA, to get to test p-values. So I'm going to repeat this over and over again. And there are reasons why. It's because these numbers fail under general circumstances. So use summary to get parameter estimates. These are the biologically significant magnitudes. Or here's how you judge whether the fit that you observed is biologically significant or not. By asking, well, how fast, does the number of D's drop per increment of body mass? So I think maybe this is wrong. It must be kilograms. So with every increase, every kilogram increase in body mass of the bird, the number of D's on average falls by 1. So that's a number that makes sense to us. And here's the standard error, and that gives an idea of, on average, how far away we are likely to be from the true value, and we can use that to calculate confidence intervals. So, as I said before, in R, use the LM function, store the results in a model object, and then apply functions to that object to extract out the bits that we want. Summary is the first of those functions. And what summary does is it takes the model object and then extracts the estimates and standard errors. Now, what is R actually doing behind the scenes? So, really what R does is there's only one X variable, but it's actually fitting 2 columns.
Would you just be able to go back to the last slide and just re-explain what the mass was, the estimate?
That's the body mass of, so the way R lays out the estimate is that first it gives you the intercept, and that's the estimate of beta 0, so that's the estimate of beta 0, B0. And mass is the X variable. And the coefficient associated with mass is the slope, so in this case, beta 1. So D's equals intercept plus minus 1 times mass, so X is mass. Does that make sense? What R is trying to do sort of behind the scenes is it's working with 3 columns of numbers. One column is the response. This column here is mass, and every row refers to a single predator species. So that's the number of D's, which we're trying to predict. Mass is the X variable. And then we also have a dummy variable here, which is just a column of 1s. And so for each value in this set here, we're sort of modeling 3.95 equals beta naught times 1 plus beta 1 times 0.07 plus the residual. And R behind the scenes will do what it does to estimate or to calculate the least squares estimates of beta naught and beta 1. Okay, so I know this seems painfully slow, you get it, but I want to emphasize it here because I'm going to show it later in a situation where it's less intuitive. So 3.95 equals beta naught times 1 plus beta B1 times 0.07 plus some residual. So every row can be described in that way. And so it chooses values of B0 and B1 that minimize the sums of squares, residuals. And model.matrix is another function that you can apply to the model object Z if you want to actually see what these columns look like. One of my reasons for showing you this is to also get you used to the idea of having a dummy column in there too, as part of the model for fitting, in this case, the intercept.
Is the value of dummy column always 1?
Very good question. I will show you this situation shortly that answers it. So there's a summary. Once again, use summary to get parameter estimates. There are a couple of packages that I want to get you used to using as well. And one of them is a package that allows you to visualize the fit of the model to the data. And it's called VisRec. I recommend it. Make sure it's downloaded on your computer before the workshop on Thursday. So this simple statement here will produce a plot with the model fit. So we gained another function applied to the model object Z to get good stuff out. So, summary for parameters ANOVA to test hypotheses. So here's an ANOVA table, and the ANOVA function in R applied to the model object will produce this as a result. And it's in the ANOVA table that you ask whether the fit is significantly greater than if the slope is significantly greater than 0. Now I want to, with this simple example, emphasize what ANOVA actually does in R, and what linear model approach involves. The function ANOVA always tests a term in the ANOVA table using model comparison. It's always asking, here's a model that includes the term, here's a model that does not include it, is this a better fit? And so it's always making a comparison between a full model, which includes the term of interest, and a reduced model, which does not. And then an F-test is carried out to determine whether the full model fits the data better than you would expect by chance. And so R actually creates sort of behind the scenes two models, which I'm going to call Z0 and Z1. And the first model drops the variable mass and fits only a constant. And this is how you would fit a mean, just using the number 1. And then the full, so that's the reduced model for a test of the role of mass, the contribution of mass. And then the full model includes mass. And what ANOVA does, if you tell it to compare explicitly those two values, it'll give you the ANOVA table and it'll tell you whether the F-test is significant or not. If you just give it Z, it will exercise its own program of action, which in this case would fit exactly these same two models, and it will tell you whether including mass improves the fit of the model to the data compared to a reduced model, which lacks it. So visually, this is what R is doing. It's fitting the model of interest and the term of interest, mass, and to investigate, is mass, the effective mass, significant? It addresses that by fitting a reduced model in which mass is removed from the model. And that involves just fitting the intercept, a constant, the mean. And then asking whether this is a significantly better fit than that. It asks whether the sum of squared residuals is reduced substantially, that we can rule out chance. So it's always doing model comparison. Okay, you already knew linear regression, but I wanted to give you sort of a picture of how R operates.
And so then you were saying when you do that ANOVA function, if you didn't break it down into doing two different model objects like Z0 and Z1, and it is just, you just put
ANOVA
it in one,
Z.
ANOVA Z,
Yeah.
it'll do that automatically.
R will exercise a program of action, which in the case of a single factor regression will be exactly what you want.
Okay.
Things get a little trickier when there's more than one X variable. R's program of action isn't necessarily the one you want.
Okay.
Multiple regression is just a step away, from simple linear regression, except now we have two X variables and the possibility of an interaction between them. So this is a data set. It's a rather small data set. Too small really to be fitting a multiple regression, but it was easy to find and to illustrate. But now we have, researchers were trying to predict the number of ant species in a series of sites as a function of the latitude of the site, the elevation of the site, and then potentially some kind of interaction between the two. So there were, I can't remember how many data points, but you're looking at them all. Not a great many, but each of them represents, as an exhaustive search for the number of ant species that are present. And so it looks a bit like linear regression, except now we have not just one X variable, but two X variables, And there's also the possibility of including an interaction between them, which means there's another coefficient whose magnitude can be estimated. And I don't know if this speaks to you, but you can imagine that if I'm standing in the corner of the room, elevation is this way and latitude is that way. And what you're trying to fit to the data points, which are all sort of hovering in the room here, is a surface. And that's what you do in multiple regression. You fit a surface instead of a straight line. Behind the scenes, there's the log of the number of species, the dummy variable to allow them to model the intercept, latitude, elevation, and then the interaction, which is literally this times this. Plus the residuals. Okay, so same structure as before. For simple linear regression, more coefficients. Use summary to get parameter estimates. Here they are. So 12, that's the intercept. There's a negative effective latitude on the log number of ant species, and a weaker negative effective elevation on the log, and then a minute interaction between those two. Those are the point estimates, and they're measured uncertainties, the standard errors, and that's what the surface would look like this. So that's what summary gives you. ANOVA is what you should use to test hypotheses. And if you go ANOVA Z, you'll get the following ANOVA table. So here are a series of tests of the three terms that are in the model. The latitude term, the elevation term, and then the interaction between the two. And each test of a term involves a comparison between two models. So a model in which latitude is included and a model in which latitude is not included. And then this F ratio measures the degree of improvement in fit resulting from including it. Same for elevation, same for the interaction. The only question at this point is, when testing, say, the effect of latitude with a model that does not include latitude, which model does not include latitude? And that's something that I want to tell you about. So if you just go ANOVA Z, R will exercise its own program of action. And it will do this by default by testing the terms sequentially. So if you don't give ANOVA an explicit full model and an explicit reduced model to compare yourself, like I did here earlier in my first example, R follows its own program of action, and these are the rules that R applies in its own, following its own program of action. First, it tests all the model terms sequentially. First latitude, then elevation, then the interaction. Why does it test latitude first? Because you wrote it first in your model. And the second part of the rule is that ANOVA respects hierarchy. So the intercept is tested first, then the main effects are tested, and the interaction is always tested last. And hierarchy means that ANOVA will never, when testing terms sequentially and respecting hierarchy, will never test the significance of an interaction, a full model including an interaction, with a reduced model that leaves out main effects of the terms in the interaction. Does that make sense? So a full model will include the interaction between elevation and latitude. The reduced model that R will compare it against will always include both latitude and elevation. It will never use a reduced model that leaves out one or both of the main effects. Does that make sense? And you might think, why would it do that? Of course, that makes sense. But actually, most computer programs don't do that. So that's why I'm taking pains to show you what R does. So with sequential testing, the order of terms in the model actually matters. So because I wrote latitude first, when I wrote down the model, latitude is tested first. And what R does is a gain model comparison. It compares a model that includes latitude, that's the full model, with a reduced model that includes only an intercept. None of the other variables are included in the reduced model. this is what I mean by sequential. So it'll test the intercept, but you don't really care about that. Then it will test latitude, and the full model will be intercept plus latitude, and the reduced model will be just intercept. Then it will test elevation, and the full model will include intercept, latitude, and elevation, and the reduced model will include intercept and latitude. That's what I mean by testing terms sequentially. And finally, the interaction. Well, the full model will include the interaction. The reduced model will not include the interaction, but it will include both of the variables that are in that interaction. It will never leave them out. Okay, so here's the ANOVA table that you get as a consequence. What if I decided to write the model this way as elevation and then latitude? The answer is I'd get different answers. And I would get a different answer in any circumstance where the design was unbalanced. So, by applying terms sequentially, it will start with elevation. It'll test a full model, intercept plus elevation, against the reduced model that includes intercept. And that's what that refers to. Then it will add elevation, and then it will add so that's the default in R. So if you've ever used LN, maybe you didn't know this. You probably should know this. This approach is called type 1 sum of squares in SAS. Now, is this all the option that's available to you? Well, no. You can test terms marginally using what SAS calls type 3 sums of squares. And if you've ever done analyses involving multivariables in SAS or in SPSS or whatever package, almost, as far as I know, all those other packages, we use this approach, type 3 sums of squares. That's the default in SAS. It's the default in SPSS. So here again is the equation, and the car package, which is a really useful one, has a function in there called ANOVA, capital A. And so we can just go ANOVA with a capital A of the object, and now the car package will follow its own program of action, but it's different than the program of action that lowercase ANOVA will apply in R by default. So, when using marginal terms, the order of terms in the model doesn't matter. You get the same result no matter what order you put them in.
Can you use the big A ANOVA from the car package with other data frames?
With other kinds of model objects?
Or yeah, just with other data sets?
Absolutely, yeah, it's incredibly versatile. And so maybe we'll give it a try at a workshop. But capital A ANOVA follows a program of action which is not sequential. Order of terms doesn't matter. Not only that, hierarchy is not respected. So, in every case, the full model that's being compared in a test of latitude, the full model includes everything. And the reduced model includes everything except latitude, including the interaction between latitude and elevation. So hierarchy not respected. Basically, the full model includes everything, and each term is tested by dropping it one at a time and leaving everything else in. That makes sense? And it leads to a different result. In fact, none of the terms are statistically significant in a capital A ANOVA. But both main effects are significant in a sequential lowercase ANOVA. So choice of sums of squares matters. Marginal or type 3 sums of squares is also called drop 1 testing, and in fact there's a drop 1 command in R that also allows you to do this. So type 3 sums of squares is the default in most computer packages. It's not in R. I want to make sure you know that. Here's a situation that we often confront where we fit data and we find that the interaction term is not significant. A common practice is to say, well, it's not significant, let's assume there's no interaction, we'll drop it, and then we'll refit the model. I can't remember if I did this. So this is a philosophy that I want to discourage you from. It's one that's actually promoted by Crawley, the author of the R book. Models should be pared down until they are minimal adequate. So fit your data. If the interaction term is significant, throw it out. Fit your data again. Any other term that's not significant, throw it out until you're left with your minimal adequate model. I want to discourage you from doing that. Maybe it's been the practice in your lab before, but there are much better ways of doing this now, and we'll talk about them later in the course in the section on model selection. How do you choose that best model? In general, though, the problem with dropping a term involves accepting a null hypothesis. It involves concluding that the coefficient really is 0. And we've just heard a discussion on what to do with a non-significant result, and the fact that a non-significant result is actually ambiguous. It doesn't mean the null hypothesis is true at all. But by dropping a variable, you are accepting that the null hypothesis is true. And that means all the other coefficients that you subsequently estimate after you drop it are biased, probably useless. So in general, a good strategy is that analysis should follow design. If the interaction was important to your experiment, you should leave it on the model. You need a very good reason before you take it out. Okay, my claim was that single factor ANOVA is also a linear model, and now I'm going to show you how. This was an experiment carried out by a group at McGill University, and it's become a pretty famous experiment because it indicates that mice can show empathy. And so what the experiment did, and this is just a subset of the various treatments, is that they would take a mouse and they would inject a mild dose of vinegar into the abdomen. And this makes the mouse uncomfortable, and it deals with this by stretching and stretching and stretching. That's the sort of the symptom of its abdominal discomfort. And each of these dots represents a different mouse and a record of the amount of time the percentage of the time they spent stretching after they were given this injection. The second treatment put the mouse together with a second mouse. And here again, each of these dots refers to a different mouse, and that the value on the y-axis is the amount of time that the mouse spent stretching. These data come from a third treatment in which the companion mouse was also injected. Now they both start stretching even more. Empathy. I feel your discomfort. Supposedly, at least that's the interesting interpretation. And what's even more, I've dropped some of the treatments, but this mouse, the companion that's injected, has to be a friend mouse. If it's a strange mouse, we're back down here. It has to be known to the individual. Don't underestimate mice. So normally we would fit data like this. It's not like linear regression because our treatments are categorical. We're comparing groups. Nevertheless, it's a linear model, and this is how we would model it in R. Same as before. Stretching is your response variable. Treatment is your explanatory variable, and fire away. The only difference, which we know, is that the explanatory variable is categorical, but we can still model it.
How do you make sure that your data is from each treatment point, that they stay within the categories in the model that you assign it? Like how does one of the data points from isolated when we go all the way to the right?
Do you mean here?
Or
Sorry, are you asking about my strip chart here?
yeah, if I don't know if they're not like I'm just wondering about the placement of the data points.
So in the graphics workshop, we did strip charts, and this side-to-side business is called jitter.
Oh.
So it just offsets them, but there's no value here. All of these points have the same x value. All of these have the same x value. So that's just a graphical convenience. But maybe the width between them could be expanded a little bit to avoid visual overlap. Yeah.
What if your treatment is only, like it's like temperature or pressure or something that's not inherently categorical, but you're testing in,
Breaking it into categories
Yeah.
and ordered categories even.
yeah.
So I'm not going to get a chance to do that, but we can model ordered categories as well. So they would be modeled as categories, as in an ANOVA. But exactly how you deal with the fact that the categories are ordered is something that I don't have time to talk about, but if your data are like that, I'd be happy to talk to you further about it. So summary, use summary in linear models to get parameter estimates, and if you apply summary to this model object, this is what you get. What are those numbers? I should explain. They're coefficients. But what exactly do they measure? Well, I'll tell you, but I want to get through ANOVA first.
Well, I was going to ask you, does the ANOVA function, I've tried using them like, it doesn't work on the testing functions, or it should?
So it's just treatment just happens to be a categorical variable. Stretching is the response variable. We fit a linear model that fits different means to different groups.
So should it work on a logistic model?
No, this is just
Okay.
ordinary
Okay.
response data. ANOVA, I'll use ANOVA to test hypotheses, and this is what an ANOVA table would look like, which we'd all recognize. Here's the test of treatment effects, the p-value, and so on. Once again, as always, ANOVA has its own program of action, and it will always compare the fit of two models every time it tests a term. And so this particular test involves comparing a full model, which includes treatment, and a reduced model that drops it. And visually, this is what the models look like. It's comparing a full model in which treatment is included, and that means a different mean to each group. And the null model in which only the intercept is present, and that just fits the same average to all of the groups. So that's the difference between the full model and the reduced model in an ANOVA. Same rules, the only difference is that data are categorical. And VisReg works here as well. It'll show you the model fit. So that's the full model. And it involves fitting a different mean to each group. Another package that I want to get you using is called EM means. And what EM means does is, oops, that should be EM mean. The package changed its name in the last couple of years. So what it's giving you is the least squares estimate of those means, along with standard errors, degrees of freedom, and confidence intervals. So it allows you to apply a function. Oh, that should be EM. I need to edit my notes now that the package has changed. But basically, all the goods are in Z. You apply this function EM means to Z, focusing on treatment, and you get all the good stuff that you want, the magnitudes, and the uncertainties associated with those magnitudes, the confidence intervals. So that's a great thing about R, is it's much easier to extract magnitudes. I just wanted to point out that the confidence intervals and the standard errors that you would get in using this are not the same as you would get if you calculated them all separately on each of the groups at the time. Because the number of observations in each of the groups is only on the order of, 12 or so. But here we have 39 degrees of freedom for testing, for estimating and calculating the uncertainty of each mean. EM means takes into account the fact that when you fit in an ANOVA, you assume the variance is the same in each of the groups. And so the variance in that group also helps me understand how much uncertainty I have about the variance in this group as well, because you assume that they're the same. So it uses the mean squared error from the total model fit in calculating these uncertainties. So it really is making use of the model fit to estimate these quantities. Okay, what do the coefficients mean? Take a deep breath. Because I'm going to show you behind the scene. You don't need to know this, what I'm about to tell you, but I'm going to tell you anyway. Because it can be really useful, and we'll use it in the workshop this week. So here's the linear model, stretching treatment. Here's our estimates. here's the coefficients table from the summary command. What do these things actually mean? What's this variable, and what do these estimates actually refer to? Okay, I'll try and show you. So behind the scenes, R codes the data into columns associated with parameters that it attempts to estimate. The data in this case are categorical, and so all of the columns in this case contain only ones and zeros. One indicating yes, that individual belongs to this treatment group, and zero, no, that individual does not belong to this treatment group. So as before, there's a dummy column for the intercept. Here's all of the y observations, but I've sort of broken them so that I can show a few individuals from the first group, the second group, and the third group. And to show you that there's now three sort of variables behind the scenes. One is the treatment is isolation. The second is the treatment is companion, treatment number 2. And third, the treatment is the injected companion. So you have a column of dummies for each variable. And a 1 indicates that this individual belongs to this group, but not those. 0, so it doesn't belong, but 1 indicates that these individuals all belong to the second group, and these individuals all belong to the third group, and not to the first or the second. Now, the one thing that R has to take account. Oh, and you can model matrix will show you what it does behind the scenes. Now, there's redundancy in this coding. So if I told you what this column was and what this column was, you would know what that column was. And redundancy is bad; it makes computers explode. So the way that R does it is it always takes the first group and then just drops it. So that now it's fitting a model containing dummy, treatment companion, and treatment companion.ing. Okay, and then it essentially does a multiple regression with those variables. So what it does is now I've dropped the first treatment dummy variable and just put the ones and zeros so that I can show you how we're modeling these values here. So here's our first individual. It's in treatment 1. So 64.4 is modeled as beta naught times 1 plus beta 1 times 0 plus beta 2 times 0 plus a residual. So every individual in the first group is modeled as beta naught plus residual. Okay, so those are the subjects in the first treatment, the isolation treatment. Second group, individuals in the second group, 56.7 is equal to beta naught times 1 plus beta 1 times 1 plus beta 2 times 0 plus residual. So all individuals in the second group are modeled as stretching value equals beta naught plus beta 1. And the third, every individual is modeled as beta naught plus 0 plus beta 2. Beta naught plus beta 2. So here are the models being fit. Essentially, if you're in the first group, this is the model being fit, a constant. What do you get when you fit a constant to a set of data? It's the simplest possible linear model, fitting a constant. And I said it's just fitting the average, exactly. What that means is, in interpreting these coefficients, the beta naught is the mean of the first group. And the second group is modeled as beta naught plus beta 1. What is beta 1? It's the difference between the first group and the mean of the second group. And the third one, beta naught plus beta 2, means that the third parameter, beta 2, is the difference between the mean of the first group and the mean of the third group. So that's how these coefficients are estimated, and that's what they mean when you ask for the summary, when you ask for the summary table. So this 0-1 scheme is R's default scheme, R's default dummy variable coding. Other programs might use other dummy variables codings. It's kind of arbitrary which ones you use, and that will just affect the interpretation of those coefficients. So as I said, beta naught, or B naught estimates the mean of the first group, 37.194. Treat companion, this is beta B1, and it estimates the difference between the first group and the second group, so this mean is a little bit lower. And then this, 20.856, estimates the difference between the mean of the third group and the mean of the first group, so that's 20 units higher than that one. So that's the interpretation of these coefficients. Now, there's two ways to treat this new knowledge that I've just given you, and one is to say, forget it, I don't really care what those coefficients are. I'm going to use EM means, and it's going to give me the means of each group, and I get that. But these numbers can actually be fairly useful. Oh yeah, just a quick thing about how does ANOVA test a term having more than one indicator variable associated with it, more than one dummy variable, and the answer is it compares a model in which the full model includes them, and a reduced model in which they're both gone. Okay, and that's why there's 2 degrees of freedom associated with the test of the treatment variable. So in other words, this comparing full and reduced model can drop any number of variables in the comparison, or any number of columns. Okay, linear models can fit categorical variables too. Use VisReg to visualize the model fits, and EM means to estimate the group means. And it's the model fitted means that are estimated. Use summary for parameter estimation. To interpret the estimate, it's useful to know how R handles the categorical variables behind the scenes. And for a single factor ANOVA, the intercept is the mean of the first group and all the others are differences. And the reason that can be useful is that you can designate your first group as the control. And so summary in this case will give you the mean of the control group. And all of the other coefficients in your table will be estimates of the difference between each different treatment group and your control group, which can be very useful. Makes sense? And we're going to try that in the lab this week, in the workshop. I haven't gone through it, but we'll do it in the workshop. There's another function which you can apply to Z, which will do diagnostics. It will check assumptions about normality and homogeneity of variances. Okay, we're running out of time. Another example, analysis of covariance. And the difference between the first 2 examples is, I've got 2 variables now. One of them is continuous and the other one is categorical. So this is an analysis of data that came out a long time ago, just asking who's got bigger brains, us or them? This is Neanderthal versus humans. So these are all estimates of brain size from fossils. And in this case, the intercept between those two, the interaction between those 2 variables is the magnitude of the difference in the slopes. But otherwise, it's just a linear model like any other. How analysis of covariance? So this analysis of covariance, and how that usually works is what we would like to do is we would like to assume that the slopes are the same in the 2 groups, so that we can then compare the average brain size corrected for differences in mass, because Neanderthals are bigger than we are, so fair is fair. They might have big brains just because they're big hulks, not because they have bigger brains, really. So size correcting is a common strategy when analyzing biological data, and usually that begins by asking, is the intercept significant? And if there is is the interaction significant? And if it is, what will often happen is that you'll maybe transform the variables. You'll try and find a scale at which the slopes really are the same, or it can be assumed that they are the same. R tests terms sequentially. If you put mass first, it'll test mass first, then species, and then the interaction between them. And generally in analysis covariance, we want to assume that the slopes are the same. And then the interaction term is dropped. And this is, really part of analysis follows design. If that was your goal, and if you're willing to transform variables in order to best meet the assumption of equal slopes so that you can compare their brain sizes, well, I did that by taking logs of everything. What's the coefficients table? In this case, the intercept is the mean for the first group, and that's us, humans. And the log mass is the slope of the common line, and then the last coefficient is the difference between the intercepts of those two lines. So again, you have to write out all the dummies in order to figure out exactly what those terms mean. But the one you're mostly interested in is this one, which is the difference between the two. So the topic for next week is going to be regression to the mean. And we'll read a paper about this and have a discussion about where it might intrude. But one place where it does intrude is in analysis of covariance. It intrudes in situations where we're trying to correct for one variable in order to compare a difference between groups. We're trying to say size correct in order to ask whether these two species, say, differ in something that we care about, like brain size or fin length or anything like that. So size correction is a pretty standard method in comparative biology. We do it all the time. But what I want to point out is, again, just a warning, and I won't be able to get into too much detail here, is that the method only works when the range of x's is actually the same between the two groups. So analysis of covariance and correcting for body mass so that you can ask whether brain sizes are different will mislead if these two groups are offset and they do not have the same mean value of x. And the reason for that is regression toward the mean. So here's an example in which two groups and the cluster of points is illustrated with the ellipses, and the long axis of the ellipse is shown in dots there. You can see that the sort of association between x and y is the same in the two groups. But regression towards the mean causes the slope of the lines fit to these data to be displaced towards the average. That's the property of regression toward the mean. In fact, it's why the method is called regression in the first place, because it has this property. But if these two groups are offset as shown here, you will detect a difference between those two groups in this y variable after correcting for body mass, but that is an artifact. And there are other methods, major axis regression and so on, that overcome those artifacts. Okay, core assumptions of linear models are just the same as the ones you learned a long time ago for analysis of variance or regression or t-tests or linear regression. The errors should be normally distributed, approximately. The variance of the residuals should be the same in all groups, and the errors should be independent. Residuals should be independent. Every observation should be independent. You have a random sample. So plot we'll use this week to explore the first two of those assumptions. Linear models, just like ANOVA we learned before, they're reasonably robust departures from those assumptions, especially if sample size is large and if the unbalance is not large. And the assumption of independence is met if you have a random sample and you have not pseudo-replicated. Just to end, I want to point out that there are, like, what if you don't meet these assumptions? We're not going to go through most of these methods, although we'll talk about some of them, but I just wanted to show you that once you get used to the linear models approach, there are sort of extensions in R that use more or less the same framework and behave in a very similar way, but can handle other situations. So, if you have outliers and things, there are robust regression methods available in R. RLM. What if your response data are binary or discrete, binomial? Well, there's GLM, or generalized linear models. What if your data are not all independent, but there are random effects and your observations come in groups? You don't want to pseudo-replicate. What can you use? The answer is, well, there's a package for that. And we'll learn about that next week. What if the residuals are not independent because of spatial autocorrelation or temporal autocorrelation or because of phylogeny? Well, there's a method for that in R as well. So this slide is really just FYI And we're actually going to try some of these methods a little bit later on. So here's the discussion paper for next week, correcting for regression to the mean. And I'm looking for presenters and moderators, and as usual, come up afterwards to let me know if you want to volunteer. And if you don't volunteer, I will use R to randomly sample names from the hat. And I'll be in touch before Thursday. I'll see you at the workshop on Thursday. This is a really important one. Linear models sort of is the outline for most of the methods that we'll be doing from now on.